Okay, so 10.4, we're finally going to start talking about what happens when there's lines and segments outside the circle. So we've talked about chords, we've talked about radii and diameter. The diameter is the longest chord, but what a secant is. So an example of a secant is line AB. So AB is considered a secant line because it hits the circle or goes through or intersects the circle at 2 points. Okay, so that's secant. Now a tangent is a line, segment, ray, whatever you'd like to call it. And I'm going to put some points here. So we'll call this D and E. An example of something that's tangent is line ED. And a tangent line hits the circle at 1 point. You can see that it's hitting it only at D. Okay, and again, only at 1 point. I always just remember it like somebody's laying down and tanning on the sun. I don't know why. And you only hit it at one spot. That just helps me to remember it. So we have some postulates, of course. So a tangent line, segment ray, is perpendicular to the radius drawn at the point of contact. So if I was to connect this radius, so again, here's a radius, I can take this radius and swing it around the circle. As it hits the tangent segment at the point of contact, and you can see this, every single time it ends up being perpendicular, every single time. Okay, so at the point of contact to the tangent line, it hits at the perpendicular. And I showed you this as well down here. I drew a tangent segment, and when I connect it to the radius, it's perpendicular. The converse is also true. If it's perpendicular, then the line is tangent to the circle. Okay, so if you have a radius and it's hitting the point of tangency and it's perpendicular, then it's tangent, not point of tangency, because we don't know if it's tangent yet, but the exterior point. This is referred to as the point of tangency. And if the radius hits that point, then we know for sure that this segment is tangent, okay? If the radius is hitting that at a perpendicular, then we know for sure that this segment is tangent. Again, tangent segment is just a segment that is intersecting the circle at 1 point. For example, AB. A secant segment, again, is hitting the circle at 2 points. So you can see it's hitting it at both E and F. So the secant segment, the entire secant segment, is referred to as DF. So that's the secant segment. Now, this is actually broken up into 2 different parts. So I can refer to this as the external part of the secant segment. Say that 3 times fast. The external segment of the secant segment. External segment of the secant segment. And then we also have the chord. So the chord is what we've been referring to. The diameter is the longest chord in a circle. And together, the external part, along with the chord, makes the entire secant segment from D to F. Okay? The next theorem, I call this the ice cream cone theorem, and it just makes sense. So if you have 2 tangent segments that are drawn to the external points of a circle, okay, and again, same external point. So we're having this, I'll do a blue. We start with this blue point here. If I was to connect these external points, these pink points, to that blue point, those blue parts have to be congruent. And again, it just makes sense because of an ice cream cone. So if you have, again, 2 points of tangency and an external point, and it doesn't matter where, okay? So it could be close, it could be far, it could be over here. And if it was over here, keep in mind that my points of tangency would not be where they were. So my point of tangency, if I was to connect this to the circle on this side, we can see that it looks like right about there, and my point of tangency right about over there. So you can see that it's hitting at these spots that were a little different than my initial ones. But again, it looks like an ice cream cone, and an ice cream cone is obviously equal on both sides, otherwise your ice cream would fall to one side. Okay, so again, if 2 tangents are drawn to a circle from the same exterior point, this same point out here, and you drew two tangent segments to hit the circle, one on the left and one on the right, those two segments have to be congruent to each other. Okay, more definitions. Tangent circles. So there's two different ways for two circles to be tangent. One of them is to be internally tangent. So you can see that this blue circle and this pink circle are intersecting at one point, which is the definition of tangent. They intersect at one point. And the smaller circle is inside the larger one. And then we also have externally tangent circles. So again, we have two circles. We have the blue and the pink circle, and they're intersecting at that one point of tangency, and those are called externally tangent circles, plural. More definitions. We also have common tangent segments. So these are tangent circles. I'm going to draw common tangent segments. Okay, so the first one is called a common internal tangent. And a common internal tangent is exactly like what it sounds like. It is a segment that is tangent inside two circles. It is common, so both of them have this tangent segment in common, and it has to go in between them, on the inside of them. So the next one is a little harder to draw. So obviously I couldn't go like this. Look at, that's not touching the circle at one point. Okay, well that's not touching the larger one. That's not touching the smaller one. So where would a common internal tangent go? And what's going to happen is it's kind of, and this is hard for me to draw sometimes, but it's going to go and it's going to pass through right about like that. So it's going to hit this circle right here and this circle right here. And you can see if I was to roll the circle in this direction, actually roll it right over here, you can see what would happen is that, again, this green point of tangency and the green tangent segment, the common tangent segment, would be inside the two circles. So you can see the blue circle and the pink circle. The green line is inside, okay, of the blue and the pink. Now, again, I understand that this was my original picture, but again, if you roll it that way, take the ball and you roll it that way, you can see that the green line stays inside. Same thing over here. Okay, I have my pink circle, I have my blue circle. This common internal tangent is on the inside of those two circles. Now, of course, I know that you're wondering, well, there must be a common external tangent then. So again, I have my two circles, and I don't want the green line to go inside them, and it has to be common. So it has to be hitting both of them. So again, what's going to happen with this line, and of course my drawing skills, look at, that's a secant, that's not a tangent, same as Botica. Here we go, something like that. That looks about right. Maybe down a little bit. Okay. I don't know what I just did. Oh boy. Here we go. Okay. So this is called a common external tangent. Again, it's common because it's for both the pink and the blue. It's on the outside of them, and it's only hitting them in one spot. And you can see it's on the outside. If I was to roll the ball, again, closer this way, you can see that the blue circle and the pink circle are still on the same side. They're both on the bottom, okay? So we call that a common external tangent. They're both on the bottom or they're both on the top. Whereas this one, one's on the top, one's on the bottom, or one's on the left and one's on the right. So that's the difference between a common internal tangent and a common external tangent. Again, going back to circles, plural, can be internally and externally tangent. And this is a common tangent segment. Circles, segment. And then, of course, you got your ice cream cone problem, tangent and secant, and all that good stuff. Okay, so we're going to get into some fun problems. Okay, so TP, I redrew it, I didn't need to. TP is tangent to circle O at T. That gives me a lot of information. If TP is tangent to circle O at point T, that tells me that, again, because I'm drawn from the radius, that this is a right triangle. The radius of circle O is 8, so I'm going to put the 8 at the circle. Tangent segment TP is 6, find OP, and obviously this is a 3, 4, 5 in disguise. So this is a 6, 8, 10. So OP is 10. Number 2, a circle with a radius of 8 centimeters is externally tangent to a circle with a radius of 18. Find the length of the common external tangent. So it's asking me to find x. The first thing I'm going to do is I'm noticing that obviously this is hitting at a point of tangency, so we have a right angle here. This is hitting at my point of tangency, so we have a right angle here. I'm also noticing that I can draw another radius to this point of tangency, bam, which means this piece is 18. And I can draw another radius here at this point of tangency, so that is also some right triangles right here. Okay, so I have my 8 and my 18. When I'm looking at a problem like this and I see 2 right angles, my instinct is to go ahead and connect a line here and create a rectangle. And so what I'm going to do is I'm going to take this 8 and carry it over here and make this part 8 as well, and this bottom piece is 10. Okay, I'm also going to say if this top piece is x, this bottom part right here is x as well. I'm going to call it the green segment. So we're going to say the green segment's x, the green segment is x, and this pink segment right here was 8. Therefore, this orange segment right here is 10. So I am working with, and I have from Q to P, this entire segment right here is 18 plus 8. So we're going to do that as 26. Now I am going to take a look at this right triangle right here. So this is a right triangle, and I see that it has side lengths of 10x and 26. If I reduce this, it's 5 blank 13. Therefore, I know it's a 5, 12, 13, but it's doubled. So this piece is 24. Therefore, the top is also 24. So this is called a common tangent problem. We will see these problems frequently. They'll probably be on your tests and your quizzes. And then the last problem down here is called a walk-around problem. So the first thing I like to do is put down my information. So they tell me that from A to B, so this segment right here is 10. They tell me from B to C is 15. From A to D is 18. And they're asking me to find this pink segment. So we don't know how big that is. And we're going to go ahead and walk around this problem. So we don't know how big this pink segment is. Now, what I do see is a lot of external tangent problems. So I see that because this is an ice cream cone problem, okay, remember if you have a circle and you have 2 tangent lines coming from the same point of tangency, point D, that means that this piece is equal to this piece. So I'm going to put that here. That piece equals that piece. The same holds true on this other side right here. Okay, this piece has to equal this piece. And the same holds true up here. This piece has to equal this piece. And then lastly, this piece has to equal this piece. Okay, so we have some congruent pieces here. And the next thing I want to do is, obviously I don't know how big any of these are, so I'm just going to call something x. Now I started here, so I'm just going to call that x and that x, because I don't know what they are. So when we don't know something in math, we call them x. Now, because this is x and the whole thing is 18, this piece is 18 minus x. Well, if this piece is 18 minus x, this piece is also 18 minus x because they're congruent. And if this is 18 minus x, then this missing piece has to be 10 minus 18 minus x. Because again, the whole blue piece is 10. I'm going to scooch this over a little bit. Okay, so that whole blue piece is 10. And so I'm actually going to simplify this right now. So 10 minus 18 is negative 8, and the negative distributed to the x as well is plus x. Again, on the top I have, negative 8 plus x, and I'm going to do the same thing. If this whole orange side is 15, then this piece has to be 15 minus negative 8 plus x. And if you go ahead and distribute that, we are going to have, sorry, it keeps doing that. Distribute this. This ends up being 15 minus negative 8, which is 23, and then minus x. Okay, and if this piece is 23 minus x, then this piece has to be 23 minus x, and I think I'm done walking around the outside. So if you take a look at this pink part right here, this is magic. This is magic math. From C to D has to be this piece, which is 23 minus x, plus this piece, which is x, for a total of 23. So even though I don't know how big x is, I can tell you right now that this entire pink segment has to be 23. Okay, and again, that's called a walk-around problem.